All right, it's now 10 a.m. and I guess we should start to keep everything on track. Welcome to this Thursday session. We have a lot of great talks lined up for today, and we'll start with Takahiro Nishimichi, who will tell us about using emulations for cosmological analysis. Takahiro, do you want to go ahead?
Thank you. Hi all, this is Takahiro Nishimichi from Yukawa Institute in Kyoto University. First of all, I'd like to thank the organizers for this wonderful conference and providing a very good opportunity for us to present our recent activities. I'm going to talk about our Dark Quest project today. Some references here. Okay. All right, let me first tell you my objectives. We wish to perform simulation-based inferences from cosmic large-scale structures. We need a good handle on the nonlinear dynamics to provide sufficiently accurate theoretical templates, and we need simulations for this purpose. Right now, on Subaru telescope, hyper-supreme cam survey is ongoing to map out the density fluctuations through weak gravitational lensing. Then, prime focus spectrograph is expected to follow up to measure the redshifts of distant galaxies to provide a map in 3D. These are excellent opportunities for us to conduct cosmological analyses. While we are fully aware of recent advances on machine learning applications in cosmology, like we've already heard from many of you in this conference, we'd like to produce something more complete. As a Japanese proverb goes, we are knocking on a strong stone bridge before crossing it. We focus on established summaries, the two-point statistics more precisely, and develop a machine to emulate them. I'd like to argue analyzing two-point statistics is already a non-trivial task. A little bit on a side story, we are so cautious that we want to be convinced with the accuracy of the state-of-the-art cosmological analysis pipelines currently available in the market. We recently called for a blind cosmology challenge to which two very strong teams participated from both coasts of the US. I have prepared mock signals of the redshift space distortion from n-body simulations with enormously large total volume for this. I provided the analysis teams with the power spectrum multiples without telling them the cosmological parameters and the precise recipes with which I populated galaxies. The two teams performed MCMC with a one-loop effective field theory template and somehow could correctly figure out at what scale in wave number k the analysis is starting to be dominated by systematic error. Finally, they sent me their most confident cosmological parameter values as the final answers, like shown in this contour here. With ground truth still, the MOX data is still available at this link here. With the ground truth still blinded. You may join the program if you have a model that you want to test. We are now thinking about extending this kind of program for more general settings, such as a field-level inference. Okay, let me come back to today's main topic. It is already 6 years since we started Dark Quest project. Our aim is very simple. We want to fully investigate the basic statistical properties of the large-scale structure as a function of cosmological parameters, especially those for biased tracers. We first follow this path from here to here, picking up cosmological parameters, perform an n-body simulation, and measure the statistical properties of interest. After accumulating simulation database, we now bypass these time-consuming procedures with a fast emulation based on the statistical model, this path. Following this fast path, we can readily perform a Bayesian inference and extract cosmological parameters from observational data. The first round of the project, Dark Quest 1, is already done, and we are now working hard on Dark Quest 2. A Python code, DarkEmulator, is now public. after applied to a two-cross-two-point correlation function analysis from HSC galaxy-galaxy lensing and SDSS both angular correlation function, which we plan to post on archive in a week or two. We have a dedicated website from which you can reach to all the related information on the DarkQuest project. The code is maintained on GitHub, and the documentation is also available, including a notebook for the basic usage. You can install it easily by these one-line commands. The results of the HSC cross-both analysis will be presented in a flash talk by Hironao Miyatake in about 2 hours. Stay tuned if you are interested. Okay, so here is the overview of the DarkQuest 1 campaign. We have selected 100 samples from 6-dimensional WCDM cosmology using a flavor of Latin hypercube design, so-called sliced LHD, where one slice with 20 samples are kept unused in training process and used for validation. The simulations were done with 2048 cube particles in either 1 or 2 gigaparsec per H boxes. And we analyzed central halos from the Rockstar Finder with mass larger than 10 to 12 solar mass and measure the mass function as well as the correlation functions, both auto and cross between halos and matter. Also, the large-scale behavior is separately calibrated using the propagator method, which is essentially a sample variance cancellation scheme by using the cross correlation between the nonlinear and linear density contrasts. Having explained the quantities of interest, the question now is how we should model them statistically. This is a simple regression problem. More precisely, we want to predict lensing and clustering statistics, which together give a data vector with a size about 100, given 6 cosmological parameters, plus about 10 parameters to specify the galaxy sample. In this regression task, of course, deep learning is one possibility. It is very popular in different fields these days. And essentially, its high expressivity together with some black magics for regularization are key to me. But it works only when a large training data set is available. However, as clear from previous slides, the size of our data set is of order a few hundreds, probably way too small for deep learning. It thus results to a more traditional regression scheme based on Gaussian process, a popular non-parametric method providing a natural way to regularize the outcomes. Also, to make our code to adapt to different galaxy populations, we put our central focus on the 3-dimensional clustering of halos instead of galaxies. The relevant statistics, such as the correlation function of halos, are tabulated, making a data vector of a size around tens of thousands, and are compressed by a weighted PCA. The coefficients of this PCA are then modeled by GPR. Finally, the 2-dimensional projected statistics of galaxies are analytically computed, assuming a halo galaxy connection model. This part is quick using FFT log. The halo galaxy connection model can be customized according to the galaxy sample of interest. Okay, let me now show the performance. I show here the halo mass function at redshift 0.55. On the left, the curves here are the 101 models with the fiducial cosmology shown in red. We then fit the measurements with a simple parametric model and residual here. Then the coefficients are of the fits are compressed into a smaller set of numbers by PCA. And finally, on the right, the GPR accuracy is shown for the training set and validation set. We achieve about 1 to 2% accuracy on low masses, but it's getting worse towards higher masses due to the smaller number of halos available in the simulations. Same thing continues, but now for the Halomata cross-correlation function, which can be used to compute the galaxy-galaxy lensing signal. I consider here halos with number density 10 to minus 4, roughly corresponding to the post-CMOS sample. Similarly to the previous slide, thus final accuracy can be checked in the right panels. Finally, the halo autocorrelation function is displayed. Due to the shot noise effect, the accuracy is a bit worse, but still we can typically reach 3% and 5% for worst cases. Before concluding, let me advertise another emulator developed using the DarkQuest1 database. This is for the redshift space clustering led by our former student, Yosuke Kobayashi, who has just moved to Arizona. Yosuke was really a hard worker during his PhD, and he could develop an emulator based on a not so deep feed-forward neural network with a simple architecture like here. And shown here on the right are the accuracy for the monopole and quadrupole moments of the halo power spectrum, with the former in blue, these tiny error bars and shades, and the red quadrupole in red. And this top one is training set, and the bottom one is validation set. The final accuracy is not so different from a GPR-based model, but the flexibility of the network design made it easier for him to make predictions of a high dimensional output values, in this case, a power spectrum table, this one, at various wave numbers k and the direction cosine mu simultaneously. The code accepts 9 numbers, cosmology, redshift, and 2 mass scales, and returns 620 numbers.
You have 1 minute left.
Finally, okay, we are so happy and proud that we can show that Yosuke's emulator is working on real survey data. You can find this paper on arXiv announced last week. We performed the full shape analysis of the both DL12 spectra and put constraints on fundamental cosmological parameters, assuming lambda CDM, after an extensive validation studies on MOX. Interestingly, the typical size of error bars and the central values are similar to those from EFT-based analysis done by Ivanov et al., despite of the completely different modeling methodologies. While it is not conclusive yet, we found sigma 8 slightly smaller than Planck, consistently to recent weak lensing analyses. Okay, I'm done. Here's a summary. Please stay tuned for cosmology results from HSC and BOSS, presented by Hironao in 2 hours. Thank you very much.
Thank you very much, Takahiro. Very, very nice work. Any questions from the audience? So while people are still thinking about this, I have a question regarding how many simulations you need to reach convergence in your training. So I think you said 100 simulations you were using. 100 cosmological parameters, right. Is that right? And like if you use 50, how do your result decrease?
So to check this convergence, we employed this design, slice Latin hypercube design. It can be used in a sequential manner. So we first put 20 simulations to form a kind of optimized design over the space. And if the result is not good enough, I can just add 20 more simulations to improve the accuracy, and I can stop when it's satisfactory. But the question is very tough to answer. I think it depends on the number of parameters to vary, and so basically it's a hypervolume. And I do not have any good measure to know a priori how many numbers of simulations are needed.
Thank you. So we have one question from Annalisa in the chat, asking if your emulator already takes into account possible effects of baryonic physics on the labeling of dark matter halos. So directly on the
Indeed, we have tested this in. Okay, so I don't have
Let's see whether that works.
slide for that, but so we have tried to slightly change the profile of dark matter halos following a simple analytic form presented based on elasticity energy simulation, I think. Maybe Illustrate's previous one. But the essence is that we just modify the halo inner profile in a way that the mass is conserved. So redistribution of the material inside the halo. And yeah, it is there, but it's not in the public version of DarkEmulator yet.
Okay, okay. Thank you so much. Let's thank Takahiro again.
Thank you.